Next talk this morning is by André Salles de Carvalho, and the title of his talk is the following question: Are generalized pseudo-Anosov mapping tori hyperbolizable?
All right, so thank you for inviting me to give a talk in this wonderful city where I happen to have been born. So I wrote down here what I want to talk about. So I'd like to start saying what generalized pseudo-Anosov maps are, and then I'll sort of briefly recap what the proof of hyperbolization for fiber 3 manifolds is, because I want to relate this to generalized pseudo-Anosov maps, and then I'll sort of change tack and try hyperbolizing generalized pseudo-Anosov mapping tori by taking limits, and I'm not going to manage, but there'll be something interesting that will come up, and then I'll end with two questions. So the first thing I'd like to say is what generalized pseudo-Anosov maps are, but I'll start with an example of so here's the easiest pseudo-Anosov map to describe ever, okay? So you start with a square, a flat, piece of paper. This is rectangular, but anyway, it doesn't matter, it could be rectangular. And then you glue this side in half like this. You fold it in half and glue it in half. You do the same thing at the top. And then down here and over here, you divide in half and fold again. Then you divide in half and fold. And then you divide in half again and fold. And divide again in half and fold, etc. Divide again and fold, and so on. And you fold this up completely like that. So the quotient turns out to be a sphere, but it doesn't matter now because the map is the following. You just squeeze vertically by a half and stretch horizontally by 2, and you fit it in here like this. So this is exactly half of the. So you fit it here like this. So it's squeezed and stretched, and then you bend. So, and then this bends like this, and you fit it here. Okay, so that's the map. And the map inside of here, the matrix is 2, 1/2. Okay, so there's a linear map inside of there. And because of all these gluings I've done here, this induces a homeomorphism that I'm going to call phi 0 of this 2-sphere. Well, this is a sphere. It's topological 2-dimensional sphere. Is that all right? So this is, to my mind, the simplest pseudo-Anosov map ever. It's just easy to make a picture of it, except that it isn't a pseudo-Anosov map because it has, so this sphere here has all these points where I've folded, and that lives in a single orbit by that map, by the way, and there are infinitely many such points. Right? And each one of these is a singularity of the foliations, if you want to think about pseudo-Anosov maps like that. So each one of these, so the two foliations here, by the way, are horizontal and vertical foliations. Okay? But at these points, what you see is something like that. Okay, so you have an infinite orbit of one-pronged singularities, which lives in a single orbit, and it leaves this point, goes like that, comes back to that point. It's called a homoclinic orbit. All right, so that's the example that I wanted to mention. And let me just say that this is a tight version of something that dynamicists know and love, which is Smale's horseshoe map. Okay? So that's Smale's horseshoe, and this is just a pseudo-Anosov-like version of Smale horseshoe, which we call then a generalized pseudo-Anosov map. Okay, so generalized pseudo-Anosov maps are pseudo-Anosov maps which are allowed to have infinitely many singularities, but with only finitely many accumulation points. In this case, there's only one accumulation point here. But let me then say what generalized pseudo-Anosov maps are more generally. So definition. So I'll start. So we'll have a S. I'll do the definition a bit like Bruno did. Is a surface with, I'll call it a conic flat structure, i.e. away from a set C, of which are going to be the cone points. This S has an Euclidean structure, and at points of C, it has a conic structure, a flat conic structure, meaning something like this, or so this is a cone like this, where the cone angle is pi, but you might have cone angle, large cone angle like 3 pi or etc. And moreover, we should have also S has well-defined horizontal, and therefore vertical directions away from C. So away from cone points, you know what the horizontal direction and the vertical directions are. And then phi now is a homeomorphism, preserves C. The cone points are invariant under phi, and there exists a lambda, a real number bigger than 1, such that away from C, phi is lambda 1 over lambda. Okay? In coordinates, these Euclidean points in the horizontal and vertical directions, it expands horizontal directions by this factor lambda and contracts vertical directions by the factor 1 over lambda. Okay, so then if C is finite, if cardinality of C is finite, so that's what we call a pseudo-Anosov map. Phi is regular, the pseudo-Anosov maps. But if C is infinite, but has only finitely many accumulations, we call it phi a generalized pseudo-Anosov map. Okay? Well, actually, I'll call pseudo-Anosov maps generalized pseudo-Anosov maps also, but typically, when I say generalized pseudo-Anosovs, I'll be thinking of the ones which have these infinitely many singularities accumulating at finitely many points. And this is the prime example. Oops. Okay, so let me just mention that generalized pseudo-Anosov maps are very abundant. So note, so every graph endomorphism, which which is Leo. Leo is locally eventually onto. That is, every piece of the graph eventually maps to the whole thing. And can be realized as a near homeomorphism. A near homeomorphism on a surface. A near homeomorphism is a map that can be arbitrarily well approximated by homeomorphisms, yields a GPA, a generalized pseudo-Anosov map on the surface. Okay, so these maps, they're very, well, you can find them abundantly in nature. Okay. All right, and so one more thing I'd like to say is that so these conic flat structures, they are nice. So conic flat structures, these, I mean, with these well-defined horizontal and vertical directions, they are good for two things. One, they induce a complex structure on S. And two, they tell you how to deform it efficiently, how to deform it efficiently. So from a conic flat structure, it doesn't even have to have well-defined horizontal vertical directions. You obtain a well-defined complex underlying structure. But if you have the horizontal and vertical directions, you can deform this complex structure efficiently and get a geodesic line in tachymeter space. Okay, so here's the line in tachymeter space, and maybe at this point here you have the square with the identifications. And if you move in one, so this is like 0. If you move here, you squeeze the vertical direction and stretch the horizontal direction. And if you move in the other direction, so this is like structure the omega 0. This is structure omega t, where t is the squeeze stretch factor. And if you do it in the other direction, you this is like W minus T or something. Okay, so, and that's a geodesic in tachymeter space. And I'm saying this for some reason I forget, but I'll probably remember along the way. All right, so this is what generalized pseudo-Anosov maps are. And then you might wonder, why not try and produce hyperbolic 3 manifolds out of these? So let me remind you of the proof of hyperbolization of fiber 3 manifolds. So this is item 2 here, hyperbolization of fibered 3 manifolds. So, right, so you start with a pseudo-Anosov map on a surface. And I'm going to be, right, let's just think that this is subsurface. I'm not saying it's compact. I'm not saying it has finite topological type. Probably does, but anyway. And then W0, so this is like phi, well, I'm not calling this phi 0 because it doesn't have to be. This is some pseudo-Anosov map on some surface. This is a conic flat structure with horizontal plus vertical directions. And then you start with some representation of the fundamental group of S into PSL 2R. And then you do the following. You take two copies of, well, right, so let me call here rho 0 of pi 1 of S is gamma 0, and you get two, so, and then X is just age 2 mod gamma 0. Okay, so now this surface that started life being a topological surface, say, acquires a Fuchsian structure, and then you take two copies of this surface and the complex conjugate of it, and you just draw them like that, perhaps. And then you put the conic flat structure over here, which has these two directions. Oops, maybe I should use different colors, although the colors don't appear very well on that thing there, right? And then you squeeze, you do this, you walk along these geodesics in Teichmüller space in one direction here and in the negative direction over there, okay? So then you walk, so let me, so let now xt and x bar minus t let be the results of moving along the geodesic, the Teichmüller geodesic in the positive plus and minus directions determined by omega naught. Okay, so this conic flat structure tells you how to move, and then you move in one direction up here, and you move in a different direction down here, and then you use this Bayer's simultaneous uniformization theorem that gets for you, so that this produces for you a new representation, rho t, of the same surface group into PSL2C now, such that now, and then, which is a quasi-Fuchsian representation, quasi-Fuchsian, and what happens with this representation is that, okay, so now this is a version of, a copy of, well, a drawing of phase 3, and the group in here, so gamma t is the group that sits here. The limit set is some quasi-circle, and this quasi-circle is becoming very complicated and trying to fill this sphere at infinity, and then there's an upper part here and a lower part to this continuity, to the what? What is that called? This continuity set. So this is the limit set, the complement of the limit set, and U plus divided by this group is this xt here, and U minus divided by the group is x minus t bar. Okay, so then what? So I've used one strong theorem, and then I have to use another famous theorem. So taking too long talking about this. So then Thurston's double limit theorem says there exists a subsequence tk going to infinity such that these representations rho tk converge to a representation rho infinity from pi 1 of the surface into PSL2C. So this is not, these are not, so they're quasi-Fuchsian all along, but the limiting representation is not quasi-Fuchsian anymore. That quasi-circle there that became extremely complicated. All right, so what you're doing here is that you lift these two foliations to the upper and lower hemisphere, and you're contracting these leaves. And as they get shorter and shorter, this quasi-circle here becomes, nearly the whole sphere, and in the limit set becomes the whole boundary sphere, right? And if gamma infinity is the image of PS under this representation, so this guy acquires an extra symmetry, or H3 modulo this guy acquires an extra symmetry, and symmetry which I'll call alpha, and then that's it, right? So now H3 mod alpha, so this is M infinity, and then so you divide by this limiting group, and then but it acquires an extra symmetry, and this extra symmetry, if you divide by it, this is the hyperbolization that you're looking for. So that's the program. So that's the summary. I'm sorry if many of you know this better than I do. But in any case, the point I'm trying to make is that, so this is a true theorem for surfaces of finite topological type. Okay? So that's how you hyperbolize three manifolds that fiber over the circle when the fiber is a surface of finite topological type. These surfaces here of generalized pseudo-Anosovs are not of finite topological type because you have to puncture at the one-prong singularities. So then the surface of the horseshoe is a sphere, but you have to take away all these singularities here, the one-prong singularities, and this in the end is going to be some surface that is going to be a sphere with infinitely many punctures. Okay, and there's there's one end. It turns out that this end, if you want to compactify these things, this end actually, the conformal structure extends uniquely across this end as well, but that's not relevant for here. So okay, so and yet, all right, so Thurston's theorem, this double limit theorem, which is a hard theorem, is proved for finitely generated groups and finite generated surface groups, and these surfaces don't have finitely generated fundamental group. And all right, and then my attempts at generalizing this proof have not produced any results. All right, but anyway, so but there's the question, right? Which can you run this proof for generalized pseudo-Anosov conic flat structures. And, okay, just make a remark that if you were able to, then you would get, well, if you can prove something, you would expect to get, in the limit, some Kleinian group which is quasi-conformally rigid on the one hand, because that's what you'd like it to be, perhaps, but also it has to have infinite covolume, because these punctures form an infinite orbit of punctures. When you take the lift of this becomes a non-toroidal end of the three manifolds. So you can't expect it to have finite volume. Okay, so let me then change tack and try a different approach. So change tack here, tack, and try to obtain a hyperbolic structure on, well, okay, so on M phi naught. Okay, so now phi naught is again the tight horseshoe, for example, or any generalized pseudo-Anosov that you like, which is the mapping torus S2 minus now C cross 0, 1 modulo phi naught. Okay, you glue the two ends of this thing. So you take the product of this with the interval and glue the two ends by the tight horseshoe. Via limits of finite volume three manifolds. Okay, how are we going to do this? How are we going to do this? Well, we are going to well, there are many ways you could try doing that, but here's one way to try. So this is the work of Toby Hall. There is a nice collection of horseshoe periodic orbits, called NBT. NBT is for no bogus transitions, but anyway, so NBT is some collection of horseshoe periodic orbits, and they're parametrized by a rational number, and Q belongs to 0, 1/2 intersected with Q, a rational number between 0 and 1/2, and with the following properties. Well, the isotopy class of phi naught minus beta Q is pseudo-Anosov, regular, usual pseudo-Anosov for every Q, okay? For every Q. So what I'm saying is the following. So you look again at that surface where the sphere where the horseshoe acts, but you don't pay attention to the cone points anymore. I'm not even drawing them in. But phi naught acts here with infinitely many periodic orbits, just like regular pseudo-Anosovs do. You know, so I didn't mention this, but it has densely many periodic orbits, as a matter of fact. And then these periodic points live here somewhere. And then for this family that Toby found, you take them out, and you look at the isotopy class of the tight horseshoe relative to these points or with the points removed, and they are all of pseudo-Anosov type, okay? So then call phi q the pseudo-Anosov map in the class of phi naught minus beta q. Well, all right, so since each one of these is of pseudo-Anosov type, well, you can construct the suspension, the mapping torus of the sphere minus these points with respect to either phi, well, the isotopy class of phi 0 or phi q, doesn't matter. And mq is the mapping torus of S, well, I'm getting a little squeezed here. Well, okay, so maybe I don't have to say this quite right now. Let me make a statement then, and then I'll go back to that. Okay, so the first statement then about these periodic orbits is the following. So theorem with Toby Hall is the following. The phi q converges to phi naught as q goes to 0. All right, so this is a pretty short statement, but what I'm saying is the following. So you look at the sphere with phi naught acting on it, the tight horseshoe acting on it, and then you take out one of these orbits beta q, and that, in the isotopy class of this, there's a pseudo-Anosov map, or you take any one of these orbits that you take out produces some pseudo-Anosov map, and you collect these in the family of phi q. So is the pseudo-Anosov map in the isotopy class of phi naught rel beta q rather. Okay, so now you have a family of pseudo-Anosov maps indexed by this rational number between 0 and a half. And what I'm saying is that this actually converges as q tends to 0 to the tight horseshoe. And this is uniform convergence, okay? All of these maps live are homeomorphisms of the sphere, and they converge, okay? So that's one statement. Now, the other statement involves hyperbolic 3 manifolds, and it is the following. So now let MQ be the mapping torus S2 minus beta Q. So you remove one of these orbits. Oh, I should have said maybe. Anyway, I'll say a word about what these orbits are. Cross 0, 1 divided by the horseshoe, or it doesn't matter, or phi q. Both are the same isotopy classes. So you produce the hyperbolic 3 manifold after removing the orbit beta q and taking a suspension or mapping torus. And then the second theorem, which is together with Sylvain Bonneau, Gonzalez, Menezes. Okay, so I learned today that Gonzalez is with 2 Z's and Menezes is 2 S's. Okay, me and Toby, that there are infinitely many different geometric limits, limits of the MQ as Q tends to 0. Okay, so this is, well, first time we saw this, I found it strange, but that's how it is. So on the one hand, the pseudo-Anosov maps on the sphere, this family of pseudo-Anosov maps converge. They're parameterized by Q, and you let Q go to 0, they converge. So in particular, what the statement is saying is that no matter what sequence of Q's converging to 0, these maps converge, and they converge to the same limit, which is the tight horseshoe. Okay? On the other hand, there are infinitely many different ways of going to 0. So let me say QK with QK. So there are infinitely many different subsequences of rationals going to 0, so that the associated hyperbolic 3 manifolds converge in the geometric sense, and they converge to different limits. Okay? So maybe I could show. So that's a plot of the limits, the limit volumes of all of these, of many of these limit manifolds. Okay? So there are some words up there that say things that, but anyways, so, and each one of these no, that's wrong. So these are the limits already. So there are, as you can see, there are infinitely many limits because it looks pretty infinite collection of dots, and they seem to have accumulation points, and that's how we prove that they are indeed all different, because looking at volumes is pretty convincing, but you have to actually prove that they are not homomorphic. So this, oh, I see. Eu apaguei? Ah, okay. So this volume here is 5.333, or 33. And that's a known volume to people who work with hyperbolic 3 manifolds. It's the volume of the magic manifold, and it's possible to actually show that limit there is the magic manifold. But there are many other, interesting 3 manifolds there. And for example, this sequence of limiting volumes, the red ones, we show that in fact they are all Dane fillings with coefficients converging to infinity of the same hyperbolic 3 manifold with 4 cusps, which is how we prove that there are indeed infinitely many which are different from each other. It's an interesting 3 manifold. No, it's not quite the smallest volume, right? I mean, it's associated. It's a hyperbolic manifold with 3 cusps, right? Yeah. And it's, I think, smallest volume among 3 manifolds or something. Anyway, so that's what I wanted to say. So I, unlike Genevieve, I will actually finish early and let everybody go to lunch, because I was threatened by somebody too that we had to be out of here before 1. But let me just say, state 2 questions here. Questions. One, so understand what happens when we run the hyperbolization proof on GPA, genuine GPA, that is with infinitely many punctures, conformal conic flat structures. And the other thing that I also find interesting is to understand the collection of three manifolds, MQ, not MQ, M beta is the collection of all suspensions, mapping tori of phi 0 acting on S on minus some periodic orbit, where beta is phi naught periodic. So I mentioned this family here because that's the one we worked with, and I was going to say something more about it, but let me just finish stating what this question is. So now look at so the horseshoe has lots and lots and lots of periodic orbits, and each one you take out, you can run this game, or it might not be pseudo-Anosov, but anyway, there are many of them. Most of them are pseudo-Anosov. And you could look at the corresponding hyperbolic 3 manifold, and you could think, well, I mean, what is the collection of all such 3 manifolds? More than that, you could even think about, oh, actually, so I shouldn't call this M, should call this script M. So this is a collection of all such 3 manifolds, and maybe you even want to take the closure, the geometric closure of this collection, and see what you get. Okay, so let me just say a word about what these NBT orbits are. So they happen to be just the simplest pseudo-Anosov orbits for the horseshoe, meaning that these orbits, or they are pseudo-Anosov orbits in the sense that the horseshoe relative to them is a pseudo-Anosov map, and pseudo-Anosov maps have train tracks. And what is special about these orbits here in particular is that the train tracks for them are essentially line segments. So they have to have these little loops. So for example, beta 1/3, the train track is something like this, like that, and then it continues here because I ran out of space, and like this and like that. But the train track is essentially a line segment that goes like this, like that, and like that. And there are loops involving the punctures, but aside from that, these train tracks are straight line segments. Okay? So, I suppose I'm sure most train tracks for pseudo-Anosov periodic orbits of the horseshoe have train tracks which have 3-prong singularities, 4-prong singularities of all types. These are the ones which don't. So that's why we single them out. And okay, so that's where I stop. Thank you.